Alrighty, well, here we go again. It's time to crank out atomic structure notes number 3. Very, very easy in my opinion. Probably the easiest of all three. Want to get started by mentioning here in the notes, right in the notes, oh my goodness, I would strongly recommend that each and every one of you watch that video. I have embedded that on our website with that heading. Really very, very well done. You'll see that again. You don't even have to click on a link or anything. It's right there on our website. And I'm going to try to highlight some of the key details of things. One of the things that we're going to talk briefly about is something called the photoelectric effect. And that would be where you shine a light, energy comes in to a surface, and how much energy do you have to put in to kick out electrons? Okay, you can kick out the outermost electrons, but if you crank up the energy, you can go beyond just the ones on the very outside. Okay, so photoelectric effect, could really talk at great length about that. Albert Einstein, blah, blah, blah. I want to use that in the world of AP chemistry. Again, take a look at that YouTube video clip. What's new to me this year and new to the AP chemistry world in general is this idea of photoemission spectroscopy. PES is how the cool people say it, and interpreting some spectra. Well, what we like about this is that it builds nicely onto the Bohr model. Here we have lithium. The Bohr model for lithium, think of the rings or the orbits. The protons are in the middle, and then we've got these electrons going around in these rings or shells or orbits. Well, the first orbit can hold 2 electrons, and so I've done that. Lithium has a total of 3 electrons, okay? And for the Bohr model, it would look like that. 2 would go on the inside orbit, and then we'd have 1 on the outside. If we look here then at the photoelectron spectra, as we call it, for lithium, what you would see would be these are the 2 in the inner orbit, or orbital, I shouldn't say orbital, that's not right. On the inner orbit, and then this would be the 1 electron on the outer orbit. Okay? Couple things to notice here before we get complicated. The y-axis shows us the relative number of electrons. This peak is larger, taller on the y-axis than this one. And that's because you've got 2 electrons there, but only 1 there. Taller peak means more electrons. Now we know that the Bohr model worked great. The Bohr model worked great for hydrogen and other very simple elements like hydrogen. And it really does a good job. If we go to what we currently know in terms of the Bohr model, if lithium has 3 electrons, 1s2, 2s1. Okay? Now if we look here, knowing what we know now, these would be the 1s2, and this would be the 2s1. Okay? If we look here at the y-axis, and let me erase this to get rid of the clutter. If we look here at the, at the x-axis, what I want you to see, this was a little tricky to me, I want you to see that this corresponds to lower energy, and this would be higher energy. You see 10, then 1, then 0.1. It's backwards of the way you might think, but there's a reason for that that I really have now come to appreciate. So really, as we look at this photoelectron spectra, we're shining a light. How much energy does it take to remove an electron? Well, out here in the land of the 2s, or the outermost, okay, those electrons are not held as tightly, and so it doesn't take as much energy. But the closer we get to that nucleus, you're going to need to bring your wallet. Don't write this down, but you're going to need to bring your wallet to remove those 1s2 electrons. If we then flip over, okay, let's keep going. If we look here at this, the Bohr model for carbon. Now carbon, I look at my periodic table, carbon is element number 6. So we have 6 electrons for our carbon. Again, in the Bohr model, we have 2 electrons on the inner ring. And then, to make things clear, I'll show the outer electrons on the next ring. It has 4. So according to the Bohr model for carbon, we have 4 electrons on the outside that would be easily lost. And then we have 2 electrons on the inside that you'd pay a little bit more energy to lose. Well, let's take a look at what the photoemission spectrum here, or excuse me, photoelectron spectrum looks like. What we would see here in the PES, as we call it, really simple. What we know for carbon, carbon is a 1s2, 2s2, 2p2. 1s2, 2s2, 2p2. If we know, there we go. If we know this, I would expect those electrons on the outside are easily lost, courtesy of Coulomb's law, because they're so far away from that nucleus. They're so far away. Doesn't take much energy to knock them out of there. Here's what we're going to do. And this technique really worked well, and I want to connect it back. But when you see peaks like this, if it's carbon, it's going to be, those are the 1s2 electrons, because that's the highest energy. Remember, energy is 100 here, it's 0.1 out there. So 100, then we go 1s2, 2s2 for the second peak, 2p2 for the third peak. Again, the farther things are from the nucleus, the looser the electrons are held. Due to shielding, and that distance is so far away that the 2p electrons are so far, far away. Don't require a whole lot of energy. But if we look at that, looky there, we have electrons with 3 different amounts of energy. This amount of energy, this amount of energy, this amount of energy. We have electrons with 3 differing amounts of energy. The Bohr model only predicts 2. Bohr model predicts 2 types of electrons. The PES graph shows 3 types of electrons. And when I say types, I mean electrons with a certain amount of energy. The PES data is very, very consistent with what you see up there, okay? And the 1s2, 2s2, 2p2. So if you're like me, you might be saying, okay, but I already knew about this. Well, pretty much you accepted it at face value because we told you that's what it was. Okay? So what we now know is the Bohr model falls short of reality. We have experimental evidence with this PES spectrum here that really confirms, hey, there are electrons with 3 different types of energy levels. Okay? Let's take a look at another example. If we look at this, and I'm not sure why it's showing up the way it is, but we're fine and dandy. Okay? As we look at this, here's what I see. I see we've got 1s2, 2s2, 2p6, 3s2, 3p. Now this one is taller. This one's taller. If this height corresponds to 2 electrons, okay, if it corresponds to 2, then I'm going to say it's got more. It's going to say 3 electrons. So I look based on 1s2, 2s2, 2p6, 3s2, 3p3. I look where that is on the periodic table, and I see that we're talking about the element phosphorus. Okay? Phosphorus because it contains all of those orbitals, and I especially want you to clue in here the height of that peak gives me 3 electrons. Okay? We could even take a ruler and we could measure the height of this as compared to the height of that. If that's equal to 6, this is half as tall. Okay? And again, I'm not sure what's going on with the computer here that the graph looks as strange as it does. Hopefully we're going to be in good shape. So that's what element, okay? Label each peak in the spectrum. I just do that. I start on the far left and go 1s2, 2s2, 2p6, because I know, boy, oh boy, do I know, if you want to try to remove the 1s2 electrons that are so close to that nucleus, you better bring your wallet because it's going to be expensive. Why is one peak so much taller than the others? It's due to the number of the electrons. Okay? And so the 2p6, you would expect that to have a much, much taller spectral peak there. Okay? Because the y-axis is, the y-axis here, the relative number of electrons. Okay? If we look here, okay, at this next one, again, same idea, and I would encourage you, if you're feeling pretty good about this, go ahead and actually stop this and see if you get the same thing that I get. And that would correspond, looking at my periodic table, okay? And so what I've got written there, the 3p1 peak is lower in height. It's lower in height than is the 3s2, okay? And you could, again, perhaps measure it to say, is it half as tall? But if that's got 2, it would have to have just 1, okay? So again, I think that's a very, very easy thing. This interpreting PES data is, I think, just very, very easy. Let's take a look at problem number 3. This one I thought was challenging. I thought about keeping it as a test question, and then I thought, nah, I feel like you ought to see what I see. If we look at this, and I apologize that yours is not in color, but I've attempted to label fluorine for you on the black and white, boron, boron, and boron. The first thing I'm going to do is let's take a look at the periodic table. What are we looking at? Fluorine is element number 9. That means atomic number 9. It has 9 protons. 9 protons. If I then look at something like boron, boron is number 5, which means 5 protons. Okay? So as I think out loud here, well, for fluorine, I would be thinking here, again, fluorine, 1s2, 2s2, 2p5. So fluorine would be 1s2, 2s2, 2p5. Boron would be 1s2, 2s2, 2p1. 1s2, 1s2, 2s2, 2p1. What they're wanting to ask here, why are the fluorine peaks always to the left of the boron peaks? What we mean is, why is it the 1s2, okay, the 1s2, fluorine is to the left of boron? For the 2s2, why is the fluorine to the left of the boron? And then again, if you want to compare the 2p5, the 2p5 is to the left of the 2p1 for boron. So it's like everything for boron is for fluorine is shifted to the left towards higher energy. So we would say that it is harder to remove the electrons of fluorine. But why? That's our key question. Why is it harder to remove? Well, here's what we've got, and this is where it just really jumps out at me. Fluorine has 9 positive protons. 9 positive protons. Boron only has 5. Those electrons, and stay with me here, if we go back to Coulomb's law, there's the distance factor, and then there's the strength of the charges. Fluorine, with its 9 positive protons, is going to draw in those electrons. It's going to pull them in closer. It can pull them in closer and hold on tighter. Okay? 9 positive protons. Boron only has 5. You might say, but boron has fewer electrons to hold on to. But it doesn't have as many positive protons. And so the larger number of protons in fluorine causes the charge on the nucleus, what they call the nuclear charge, to be greater. It holds the electrons closer, physically closer to that nucleus. Okay? So those electrons always seem to be a little bit harder to remove. So you see the 1s electrons are pulled even closer to the nucleus. Okay? Same idea applies here when we compare the 2s's. Boron's it just doesn't have as many positive protons, or as many magnets, if you want to think of it that way, to hold it in closely. Okay? So again, it goes back to Coulomb's law. I think this is a rather challenging question. I think what you can expect to see in general would be, hey, here's a spectrum, you tell me what element that is. Hey, here's a spectrum, you tell me what element that is. Okay? So we want to make sure that we're good with those types of things. Okay? Well, that is it. If you've been with me through everything today, then you are good to go. You have done notes 1, 2, and 3. Again, I think I would really, really like for you all to watch that. I think this is a very well done type of thing. But you know where I am and you know what I can do. Hey, thanks for watching. Have a great afternoon, evening, or morning whenever you are, wherever you are. Thank you. Bye-bye.